everyone, welcome. So today we're going to look at the final and third piece of factoring. So if I haven't explained this before, we're looking right now at factoring in three different pieces. So imagine a puzzle, and the puzzle's made of three pieces. The first piece of the puzzle was when we did the GCF, the greatest common factor. The second piece of the puzzle is when we made that X. And now the third piece of the puzzle is going to be called a difference of squares. And of the three, this is the easiest one, but I always find that the easiest one tends to be the most difficult one because we tend to think it should be tougher than it is. So in your packet, where you should be is on page 3. And we are going to first go over, do we know our perfect square roots? So that is where we are starting right now. Okay, so when a number is considered a perfect square, and as I look around, I'm trying to grab a pen. When a number is considered a perfect square, that means when I take the square root of that number, it has a nice answer. It doesn't have a decimal, it doesn't have a fraction, it's something that we could do. And I'm going to show you a couple of resources that you should have printed out that you can use also. So here we go, bottom of page 3. So when you look at this list, for instance, if I ask you what the square root of 36 is, what I'm asking you is what number times itself, so like 1 times 1, 2 times 2, 3 times 3, what number times itself could give me 36, and that would be 6. So the square root of 36 is 6. If I asked you for the square root of 81, what number times itself would get you to 81? Well, that would be 9 times 9. So for instance, the square root of 9 is 3, the square root of 25 is 5, the square root of 100 is 10, and maybe you're starting to notice a pattern. And so we can quickly fill this in. The square root of 1 is 1. The square root of 4 is 2. 16 gets 4. The square root of 49 is 7. And then hopefully now you definitely see, whoops, I messed up. So this should be 11, sorry, and this should be 12, and this one should be 13. Now there are many other square roots, and so one of the things I wanted you to have printed up, again, just looking, because I think I have these things in front of me, and I don't, is this page. So this is your factor sheet, but the other side is the multiplication. And if you look at your multiplication page, hopefully you notice that this diagonal that's in bold, that stands out, these are the perfect squares. So if you want to know what the square root of 9 is, you can either look left for 3, or you can look up for 3. Or if you want to know what the square root of 64 is, look left for 8, or look up for 8. So this is the best way to find your square roots, and this one actually has perfect squares up to 400. And my list stopped at 169, so you get a few more on there as well. So there's one square root that I haven't addressed, and what happens with the square root of x squared? So what I'm going to do is talk about another way you look at these square roots. So I just got to switch some paper out. And earlier, or just a few moments ago, I told you that the square root of 49 is 7, and I'm going to put that 7 over here. And the square root of 64 was 8. Or, for instance, the square root of 4 is 2. And what I want to do is rewrite 49 to look a little different. So I'm going to keep that square root, but instead of 49, I'm actually going to write it as 7 squared, because 7 squared, 7 times 7 is 49. So these are the same thing, they just look a little different. And I'm going to rewrite 64 as 8 squared, and I'm going to rewrite the square root of 4, I'm going to put a 2 squared, because 2 squared is 4, 8 squared is 64. So in math, there's actually a lot of invisible numbers. So some of the practice that you should have done would have had, or would have looked like this, for instance. This is something you would have factored in a problem. And there are invisible numbers. There is an invisible 1 here, there's an invisible 1 here, there's an invisible exponent of 1. So there's a lot of invisible numbers in math that they don't write. And one invisible number is happening here. And so when we call this 7 squared, hopefully you realize that when you look at this, you call this a square root. So what's invisible is this 2 that implies, that makes it a square root, because later in math you're going to see that you could have a 3 here and you can call it a third root, or you could have a 5 here and call it a fifth root. So when you don't see a little number here, there's actually an implied 2. Understood? It's just invisible. So what happens is a square root and a square cancel each other out. So this check mark, this square root, cancels out the square, and that's how we get 7. And the square root and the square cancel each other out, and then you get 8. And then the same thing happens here, and you get 2. So that's another reason to explain why the square root of 4 is 2, because of what's happening here. So if we just try some other random numbers, what's the square root of 21 squared? Well, hopefully you'll see this pattern, and it's just 21. Or what's the square root of pi squared? Well, you just get pi. I could even throw a fraction in there, 7/8. What's the square root of 7/8 squared? It's just 7/8. And so the final one that I need for you to understand is what's the square root of x squared. And the same pattern will be happening where this square root will cancel out the squared, and we're just left with x. So going back to page 3, x squared, the square root of x squared is going to be x. So the next part goes pretty fast. We're going to switch to page 4, and we're just going to look at the problems on the left. And I do need to change this problem, so I'm going to get rid of this, and I'm going to change it to look like this. So take a moment, write it down. Remember, you can always pause the video. But the last piece or puzzle to factoring is called the difference of squares. And although it's simple, it has very strict rules to it. First of all, when you're factoring, it can only have 2 terms. Remember, terms are the things that are separated by addition, subtraction. So x squared is a term, and 81 is a term. 25x squared is a term, 36 is a term. So that's why I'm only going to be doing this column and not this column, because these all have 3 terms. All right? The other thing, it needs to be difference. Difference in the math world means subtraction. So I should see a subtraction sign between these 2 terms as well, which these all do. And then the last thing is the 2 terms that we're looking at should be a perfect square. So when I take their square root, I get something nice. I wouldn't need a calculator. I wouldn't get a decimal or fraction. So let's just start with these. So I can already see that they have 2 terms. They all have the difference. They all have the subtraction. So now we're just going to check all of these real quick and make sure they have nice square roots. So the square root of 81 is 9, and the square root of x squared is x. And that's all I'm going to do right now. Over here, the square root of 36 is 6, and the square root, we got 2 parts. So the square root of 25 is 5, and the square root of x squared is x. So far these are all working. Square root of 49 is 7, and this time I'm just going to do the square root of the whole thing, and the square root of 4x squared is 2x. So now that it's met all those conditions, the factors are really easy to set up. So I'm just going to start with this problem. So if I'm not your teacher, some of the language I'm going to be using right now doesn't make sense. But we're going to go from standard form to factored form. That should be making sense. In my class, we call the factors the neighbors, because this neighbor meets this neighbor. And don't worry about it if you're not in my class. But what's going to happen is our neighbors, our factors, are going to be identical, almost. So they're going to be twins. So I'm going to take 2x and 7 and put them inside. And they're going to become the terms of my factors. So right now they're looking like twins, pretty much the same. But we're not going to have these be identical twins. We're going to have them be fraternal twins, which makes them just a little bit different. And the way they're going to be different is we're going to have a plus and a minus. And now we're done. We have found the factors, or factored form, of 4x squared minus 49. So this is our final piece. So for this one, I'm going to make my factors, and then I'll put my terms in. And I got to have them look a little different, so I'm going to put a plus and a minus. And it doesn't matter. This time I can put the minus first and then the plus. It doesn't matter. And then for this one, x plus 9. Then the other one has to be x minus 9. And that's a difference of squares. So next week, what's going to happen is you are going to put this whole thing together, this puzzle of these 3 different ways you've learned how to factor. But that's for a different video. So let me just show you why these work real quick. And so what I'm going to do is, I went from, here it is, standard form to factored form. What I'm going to do is actually show you if we do the multiplication here, the distributing, we'll get back to standard form. So We're going to distribute 5x to 5x and 5x to 6. So 5x times 5x, there's 25x squared. So you can start to see that we're getting some of our original problem back. And then 5x is going to distribute and multiply to 6 and give me 30x. So now the negative 6 is going to distribute. And what I do is when I start a whole new set of distributing, I start a new row, and anything that's alike, I stack my like terms. So negative 6 and 5 make negative 30x, which I'm just going to put under its term that it's alike because eventually I'm going to have to combine those. And then when negative 6 meets 6, that gives me a negative 36. And then this was your last chapter. This was chapter 7, Showcase of Learning number 3. This can just drop down. And when I go to combine these, what I hope you see is that with a positive 30x and a negative 30x, they, as we like to say, cancel each other out. And then this minus 36 can just drop down. So as you see, I go back to standard form, and that's what we're doing. We're just making equivalent versions of the same problem. And so what I did to explain that to my class is if I gave you a fraction of 1/2, and I asked you to give me something that's like 1/2, I got the answers of 2/4, I got 50 over 100. These are all equivalent. They're all the same. They just all look different. And then I asked them, well, what's the decimal version of 1/2? And they said 0.5, 0.5. So these are all equivalent. They're all the same, even though they look different. And that's what's happening here. This standard form is equivalent to this factored form. They just look different. So that's that. At this point, you probably, if you're following the remote learning part, have a page that goes with it. So give me one moment. Sorry. And it looks like this. And so it says factor each completely if possible. So I ended up doing 2 problems with my class. I'm just going to share those 2 problems with you. So this is all a difference of squares. It's 2 terms. Check. Its difference. That's the second thing we need. And these both were perfect squares because I could find their square roots. And then I made one 4x plus 7, one 4x minus 7. And then we're done. I don't want you to multiply these 2 together to get back here. We don't need to check our work on this. The other thing the directions are going to say is factor each completely if possible, because there's going to be 2 problems on here that you actually can't factor. And I'm going to show you one of them. The one of them's on the left side, and it's number 5. So number 5 meets all the characteristics. It has 2 terms. I know this one's square root. I know this one's square root. But what doesn't work is there's a plus sign here. So what we're going to start to experience is eventually we're going to have problems that aren't factorable. So we're going to put an answer of N for not and F for factorable. And that's it. That is the lesson for difference of squares.